Hello, everyone. Uh, Welcome to Calculus 1 Summer 2025 class. My name is Dr. Ziqin Feng. I'll be the instructor of this class. We have another grader. I will post his information on the canvas. Um, in this video, we will discuss the syllabus of this class and how our class will be structured during the summer. And because this is a full online class, so I will post the videos on Canvas every day from Monday to Thursday. So you are required to finish the video and also do your homework before the due date. And because everyone has different schedules, I will not hold regular office hours. If you have any questions or any where you don't understand or any concerns about your work, right, about your grade, please email me for appointment. So my email is on the syllabus, which is zzf0006@auburn.edu. And the second section is the information of the uh, textbook, right? Try the or barcode. You can check out more about all access information. Every we will use WebAssign to do our homework, and also there's an ebook on website. So uh, you can check out more information on through the barcode here. And there will be two tests and one final exam. Test one will be on June 20th, and test two will be on July 30th, and final exam will be in the first week of August. So in all these exams and tests, you need to submit your work on Canvas for partial credits. And also, all the tests and the exams should be proctored in person. I will discuss how we do the in-person proctoring in a different file. And so far, this is how what's our grade policy, right? We have two tests. Each one of them is 20% of 25% of the overall grade. Final exam is 40%. Final exam will be cumulative. Website will be 10%. So that's how we will arrange the grade of the this course. And so if you have some reasons, official excuse, you cannot make it to the test one or test two, right? During that day, you can email me. We can arrange a makeup for you. Um, Let me mention this one more time. For test one, test two, final exam, very importantly, you need to submit your scratch paper, which include your work, right? Submit your work on Canvas. You can take a picture or take a picture, make a PDF file and submit it on Canvas, right? There will be a category of scratch work submission and submit it there. And in that case, you get partial credits if your answer is incorrect. We still offer you lots of partial credits as long as you are using the correct formulas or correct way to solve the problem. Okay, now let's see how do we uh, do the test in-person proctoring. right? There is a document on Canvas, which is in the first announcement of the class. Let's open that here. There is a one document which is our syllabus. The other one is some instructions for the online proctoring, right? There should be a person, right? In-person proctoring. Also, all the communications will be through Canvas or emails. And so please follow the Canvas closely. Check the recent update and also some changes or homeworks due date regularly. If you have question for that, just email me. We can discuss it. We can set up a appointment on Zoom to discuss your questions or comments, address your concerns. Okay. So this is a document about uh, how to sign up for the test, right? And so every task should be proctored in person. So if you are in Auburn, you can use the free service offered by the Big U Testing Center at Auburn University. And also, uh, lots of local libraries. If you are not in Auburn, lots of local library also offer free proctoring with the appointment. You can do that through the smarter proctoring. If you are using some private uh, service, there will be fees, typically between $25 to $60. And so, how do you sign up? And in the canvas, you just click the smarter proctoring. And so, right, if you are not at Auburn, change it to your local locations, and so you can catch up uh, the local library, right? And so if you just look for the place which is close uh, to your wherever you live now, you can do that in a library or some other private service as long as that service center is listed in smarter proctoring. And what's most important, um, always try to write down all your answers and your solutions on the scratch paper and try to label that uh, orderly, right? And in the end, take pictures, make it a single document, and upload it on Canvas for possible partial credits. So you can check out this document by yourself on how to uh, how to find a proctor, right? For yourself, whichever is convenient for you. And both document, syllabus and this document is on in the first announcement. And so I hope you have a general idea of how our class will proceed after this video. And okay, any questions about the structure of the class, email me and talk to me. We can address your concerns or questions in that way. In this video, we'll discuss what is functions and the functions, some related definitions, examples. I hope by the end of this video, you will have a decent understanding of what is function. And given a function, how do you find the domain of such a function? And yeah, right. So what's function, right? And a function is basically a rule, right? Let's give a notation first. So in all our class, we say that R here, R is the set of real numbers, right? R here is the set of real numbers. So that's our uh, notation for the whole class. We always use R with an extra line to represent the set of real numbers, and sometimes we do use from negative infinity to positive infinity. So that's another way to say that we are considering the set of all real numbers. So what is a function? Function is basically a rule, right? Function. The rule here is given an arbitrary number and from one set, this rule assign a unique number to this number, right? So the first set is called domain. So D here, there are things related to a function. D here is a set, is another set. So DE here are uh, are subsets of R here, right? For example, subsets could be from -1 to 1, 0 to 1, right? Some intervals. And we can use picture to visualize it. So this is our set D, right? This is our D. We have another set which is E, intervals, right? So this is our E here. So what does a function do is giving an arbitrary x inside D here, and D here is called domain. Domain of such a function, right? Pick an arbitrary domain of such an arbitrary element in the domain of this function. This function, the standard notation for a function is f. We call that f. Our function f is a rule, right? A rule assign another number to x. The other number is coming from domain, codomain of D, which is E. That number, the notation for that is what? Is f of x. So this is our f of x, which means f assigns f of x to x, and where x is coming from D, which is the domain of our function, right? And f of x is another number, which is corresponding to the image. You can call that image of x under f, right? They are both numbers. So let me write down the definition here. So a function, this lowercase f here, is a rule, right? It's basically a rule here, uh, which assigns assigns uh, each x in D, right? A unique element and uh, a unique uh, element. We call that f of x inside E, right? Let's try to visualize it better, right? That's our definition here. Let's see an example here. A way to try to write down concretely what does our function look like, right? Suppose your D here is a good set. For example, D here contains 1, 2, 3, 4, four numbers, right? And E contains three numbers. Let's say that 7, 8, 9, right? We can make a function maps 1 to 7. That's it, right? Remember, each function can assign a unique element to arbitrary number from D, right? But you can assign two different number to a same number in the codomain. So 2 here can also be mapped into to the number uh, uh, 7, right? And 3 can be mapped to 8, and 4 can be mapped to 9, right? So this function here is actually a collection of pairings, right? This function here, this is our f here. So our f is actually a, a collection, a set of pairings, right? This is corresponding to 1 mapped to 7, and 2 also map to 7, and 3 map to 8, and 4 map to 9. So that's basically what does a function look like. Function here is a collection of pairings coming from the first coordinate is coming from the domain. The second coordinate is coming from the codomain, right? So let me write down some traditional notation for functions. So notations we normally use F, G, H to represent functions, and we want to use xt. So the letter representing the number coming from domain is called variables, right? Or free variables, right? Or independent variables. So these two here represent independent variables, which means when you try to choose your numbers from the domain, you can choose it arbitrarily, right? But after you choose X or T, the image, right, is fixed, right? We use our use the letter and Y, normally YS here represent dependent variables. So y depends on x, s depends on y. So you can call the function to be y equal to f of x, right? F is consisting all the pairs x, y, such that y equal to f of x, right? The dependent variables. And another way to do that, you can write down y equal to f of x, representing a function for any x coming from the domain. You get a number y coming from the codomain, right? F here is consisting of all the x, y's ordered pair such that y equal to f of x, right? You can put all the x, y into the xy plane. You get a graph of such a function, right? Okay, so you can see that for a function, a very important component of a function is the domain, right? So what's our way to decide the domain of a function, right? So here's our convention for the domain here. So it's domain convention, right? So again, here we use the same notation. We let f here be a function, right? With domain E, right? But sometimes you want to get the domain through the function representation, right? So the domain of f normally in our class uh, is the largest possible set of x such that what happens and such that first requirement is f of x uh, is well defined, well defined. And second, uh, x f of x uh, are meaningful, right? For example, if your f representing an area, then f of x cannot be negative, right? So from some practical view, these two numbers must be meaningful. So these two numbers uh, are meaningful. So this is the part in the later section in the application, we'll use the second part. So far, our requirement is f of x has to be well defined. So let's see a few example. A few example to figure out the domain of a function, right? And examples. So first example here is f here is defined by the equation. By equation, y equal to 1 over x minus 2, right? You can write this as f of x equal to 1 over x minus 2, same thing, right? We want to find the domain of f, right? Find the domain of f, right? So you can see that this function has no practical meaning yet. So we just want to get all the x such that f of x is well defined. F of x is basically 1 over x minus 2. Now you can see that by our understanding of algebra. If you have a denominator cannot be 0, right? Now you can see that uh, in this case, f of x is undefined when x equal to 2, right? If you plug 2 into the function, you get 1 or 0, which is not a well-defined real number for sure, right? So the domain of f here, sometimes we write this as what? As just the DOM of f, right? And this is all the x such that x cannot be 2. If x is 2, this is undefined, right? So that's how do we figure out the domain of a given function. All we need to do is identify all the x's such that the function is undefined at that x. It's just to exclude all that uh, x values, you get the domain, right? Now let's see another function, another example here. Second example, our function here is defined by the formula, so we don't want to write down the wording, right? Just our function is given by f of x equal to square root x minus 2, right? This is same thing as saying f is a function defined by y equal to root x minus 2, right? We want to find the domain of such a function. The domain of this function, f, right? So how do we do that? As we said, we are looking for the x's such that f of x is undefined. Now you have a square root. We know that we cannot take a square root of negative number, right? So we know that f of x is undefined when x is what? Less than 2, right? Or you can say x minus 2 is less than 0, right? So then we get our conclusion here is the domain of this function is all the x such that x is greater or equal to 2. Or we can write this is from the interval form and from 2 to power to infinity with 2 included. That's another way to this set, another way to represent this set. Okay, that's good. Now let's see one more example, right? I hope by the end, after we discuss our third example, then you have a better understanding what is a function, how do we find the domain of a function, right? So the third example here, let's use a different letter for our function. G of t equal to here t is the domain, t is the independent variable in this function here, right? This is equal to square root 3 minus t and plus square root uh, 2 plus t, right? So that's a function. If you plug it, if you get a number t, all you need to do is calculate 3 minus t and take a square root, then plus the square root of 2 plus t, you get an image of that number. So that's a rule to assign a number to another number, right? And also we want to find the domain of G, right? So again here, by our discussion, we know that we are looking for all the t's such that G of t is well-defined. So the other way to do that is you are looking for all the t's, G of t is undefined, right? So you can see that in this case, G of t is undefined uh, when uh, 3 minus t is less than 0 or 2 plus t is less than 0, right? Either this happens, you get a negative number under square root, right? So which means this function is undefined. If you solve for them, the first one said is equivalent to say that t here is greater than 3, right? And the second one here says t here is less than negative 2. To make our g of t well-defined, you need to make sure t is greater or equal to 2 and less or equal to 1. Or we get our domain of g here. So the domain of this function, g here, is all the t's. T has to be uh, less or equal to 3. In the same time, also has to be greater or equal to negative 2, right? So that's the domain of this function. And if you want to write this as an interval form, so this is from negative 2 to 3. So that's the domain of this function. In this video, we'll discuss some fundamental properties of functions. And for example, what is odd function? What is even function? And I hope by the end of this video, you will have a good, better understanding what is function and also what does some function behave, right? Some behavior of some interesting functions. Okay, so right. So the first property we want to discuss is the symmetric property of a given function, symmetries. Right? What is symmetric property? So basically, if you have a function which is symmetric about some lines, right? You can, if you know one side of this function, how does that function behave? You just do a reflection, right? So the first function is the first property is called even function. So let's say that we have a function, right? So let uh, f here be a function from d to R, right? R is a codomain, right? And D is a domain. Now, because we are talking about symmetric property, we have a requirement here. So such that if you have, okay, such that D here is symmetric, right? What's the meaning of that is whenever you have X inside D implies symmetric, which is negative X is also inside D. We are talking about is symmetric around 0, right? -1 is in the domain, 1 is also in the domain, right? So we say that F here is even. F here is even, right? If F of negative X equal to F of X. And for all X inside D, right? So now you can see that if X, F of X is in a function, then negative X, F of X is also in a function. In this case, it's not hard to imagine the graph of this function is symmetric about y-axis, right? So a function look like this. An example for an even function is y equal to negative x squared or x squared or negative x squared, both even. Let's just use x squared, right? Now you can see that, okay, just note what is a negative f of negative x, which is negative x squared, right? And so this is x squared, right? So that is an even function, right? If this is even function, the graph of this function look like this, right? We know the graph of this function is the parabola opens up. And so the graph of this function look like this. Parabola opens up, right? So this is y equal to x squared. So we should know that this is a general property for even function. As long as you have an even function, the graph of such a function is symmetric about y-axis, right? Let me write that down. So in general, the graph of an even function is symmetric about y-axis, right? So that's even function, right? There are many examples. For example, cosine function, right? And so another symmetric property we have is we say f is odd function if f of negative x equal to negative f of x for all x inside D, right? There are many examples of odd functions. Let me write down one of them as an example, right? Y equal to x cubed. You can see that with the odd power. That's an odd function. Why this is odd function? Just note that negative x cubed is nothing but negative x cubed, right? So which means f of negative x is negative f of x, right? And if you try to sketch the graph of this function, the graph of this function here is something look like this. You can see that if you rotate your graph 180 degree surrounding the center, which is 0, 0, you get overlap. So when this happens, this is called symmetric about the origin, right? So we can write down the property of a general odd function. So in general, the graph of an odd function is symmetric about the origin, which is 0, 0 in our case, right? Okay, so that's two nice properties of functions, right? Being even or being odd. If you know the other, on the right side of 0, what happens? You know the left side, right? Being even just symmetric about y-axis. Being odd is symmetric about the origin 0, 0, or you can rotate your uh, graph 180 degree, right? You get the other half. Okay, another interesting property of function is basically, yeah, we will discuss this a lot. Increasing or decreasing, right? Monotonity of a given function, right? So again here, let f here be a function from D to R, right? And so this is DDR domain, right? And um, yes, here we don't need to require D here being symmetric because monotonity is about function getting bigger and bigger or getting smaller and smaller. This is very interesting because suppose your function is a stock value, right? You want to know when the function is getting larger and larger, right? Or right, or some other function, right? That's one thing we care, right? So let's take a subset of D, right? And this function may not be always increasing, maybe increasing a smaller set. Uh, uh, E here be a subset of D here, right? On the domain, some were increasing, some were decreasing. So we are looking at a smaller set of function. In this set, function is increasing, right? So we say uh, f here is what is increasing on E on the smaller set. If what happens if f of x1 less than f of x2 for all x1, x2 inside E with x1 less than x2, right? The function is getting larger and larger. So a graph of an increasing function look like this, right? suppose this is our e. Increasing function is as function getting bigger, x getting bigger, y is also getting bigger. So that's increasing. In the same time, we want to know decreasing, right? So we say that f here is decreasing on e if what happens? If f of x1 is greater than f of x2, right? Function value is getting smaller as x is getting bigger, right? For x1, x2 in E with x1 less than x2. So that means x getting larger, but function value getting smaller. If you try to sketch a graph of such function, it's something like this. I suppose, again here, this is our E here. Decreasing means function behave like this, right? So this is decreasing. So that's two other properties, the function being increasing or decreasing, right? Okay. So there are also some other kind of properties, right? Examples. Now let's see the third kind of third another kind of special function here, which is called piecewise function. Let's discuss it using an example. So what's the meaning of that is we don't have a good formula for this function overall. So in each smaller piece, you should have a different way to uh, write down the formula of this function, right? So let's see this example here. So we want to sketch the graph uh, of the following function, right? So we have a following feature as a piecewise defined function. I try to do that. Our function is given by y equal to the absolute value of x, right? When x is less or equal to 1. And also equal to 1 when when the absolute value of x is what? Is greater than 1, right? So that's our definition f, right? If you plug x into this function, you get a y out. For example, if you plug in 1000, y will be 1, right? Plug in 0.5, function is 0.5. Plug in negative 0.5, function is 0.5, right? Apply the formula, right? We know that in general, if you have a real number, so this is absolute value, it just means this is equal to a when a here is a non-negative, or negative a when x is less than 0, when a is less than 0, right? So, okay, let's rewrite our formula in a different form. I mean, the function in a different form, right? And so we know that um, let's try to do that, right? So try to divide our domain first, right? So x less or equal to 1, the absolute value of x less or equal to 1 means x is between -1 and 1, right? So absolute value of x is greater than 1 means what? Means x is greater than 1 or x is less than -1, right? Apply these formulas. We can write our function in a better a way which is easier to understand. So this is -x. Okay, let's try to do that. -x when x is between -1 and 0, right? Is x when x is between 0 and 1. And when x is less than -1, the function value is 1. When x is greater than 1, function value is also 1, right? So that's a rephrase our function, make it easier to understand, or we can sketch the graph, right? So the graph of this function looks like this. So between 0 and 1, it is just equal to x. So that's just something like this. On the right side of 1, this is function is a constant, always 1. From -1 to 0 is a line with slope -1, or something like this. On the left side of negative 1, function value stay at 1. So this is our function y equal to this piecewise defined function, right? So we divide it into smaller and smaller intervals. We can discuss different function value over them. Okay. I hope after this video, you will have a better understanding of functions and domains and graph, right? Two nice property. One is about symmetric property, odd and even. The other one is about the function monotonity, right? Increasing or decreasing functions.